Good day and welcome back for part 3 of our discussion on differentiating logarithmic functions. Let me begin by reminding you of the two key formulas we introduced or discovered in our previous videos. The derivative of the natural log is 1 over x, and then that associated anti-differentiation formula is that the indefinite integral of 1 over x is the natural log of the absolute value of x plus c. Also recall from our previous section when it comes to differentiating exponential functions. So if f of x is equal to a to the x, with a being a positive quantity, then the derivative of a to the x is the number f prime of 0 times a to the x. And this is a somewhat unsatisfying formula in the sense that it depends upon this number, f prime of 0, and we're not quite sure what number represents f prime of 0. But it turns out that we can use properties of the logarithm to come up with a much more satisfying version of this formula. That is to say, we are going to determine what number represents f prime of 0. So in this case, what we would like to do is just directly differentiate a to the x. And in order to do so, we are going to write it in a more convenient form using properties of logarithms. So a to the x, the troublesome part of a to the x when it comes to differentiating is having x, our variable, in the exponent. And the natural log can very conveniently handle this for us. Note that if we had the natural log of a to the x, then x, this exponent inside the natural log, can be pulled out front as a constant. But these two quantities are not equal to each other. If we are going to take the natural log of a to the x, we in a sense need to balance that with an exponential, so e. If we now have the quantity e raised to the power natural log of a to the x, you would note that this is okay because the exponential and the natural log are inverses of each other and hence cancel each other off. So continuing on, we can rewrite this in a more convenient form as e raised to the power x times the natural log of a. And note that this natural log of a quantity we have is simply a constant or a number. And one last observation to make is when it comes to differentiating e raised to a function, we can do this very quickly, very efficiently using the chain rule. We take the derivative of the outside function, evaluate it at the inside, multiply it by the derivative of the inside. Let's put this all together. To differentiate a to the x, we are going to write it in this more convenient form. That is e to the x natural log of a. And when it comes to differentiating e raised to a function, we know precisely what this derivative will be. We apply the chain rule. Differentiate the outside function, evaluate it at an inside function, multiply it by the derivative of that inside function. But remember in this case, natural log of a is simply a constant. And the derivative of x times a constant is simply that constant. So what we are left with is e to the x natural log of a times the natural log of a. And I just want to rewrite this in an even nicer form. Note e to the x natural log of a, that's precisely what our starting point was. E to the x natural log of a is simply a to the x. So this e to the x natural log of a we are seeing is a to the x. So we're left with a to the x times the natural log of a. And note, earlier we said this previous formula for differentiating a to the x was somewhat unsatisfying because it involved this unknown number, f prime of 0. Well, now we know precisely what that number is, natural log of a. And that leads to the following new formulas. The derivative of a to the x is natural log of a to the x. Similarly, we can also use this to anti-differentiate a to the x. By inspection, I'm going to say it's 1 over natural log of a to the x plus c. And just to make sure we're all on the same page, we could easily verify or check the accuracy of this formula. And we can check by differentiating and making sure that we get back that integrand. So let's go ahead and just check this purely for fun. If we differentiate 1 over natural log of a to the x, and if we get back a to the x, we will have checked the validity of this formula. So 1 over the natural log of a is a constant, which can be pulled in front of the derivative. And a to the x can be differentiated using the above formula. It's simply the natural log of a to the x. So note the natural log of a over the natural log of a cancel, and we're left precisely with that desired integrand, so we have checked the validity of this formula. Let me also give you one more quick reminder, kind of just for fun. The natural log of e is equal to what number? And hopefully you said 1. And with that in mind, the above formulas match up with our previous formulas for differentiating e to the x. We saw previously that the derivative of e to the x is e to the x, and the antiderivative of e to the x is also e to the x. And this matches up with our above formulas because the natural log of e is simply the number 1. So let's go ahead and practice a few examples using these more general formulas. So to practice our 2 new formulas, we see the 2 examples on this current page. And I would strongly encourage you to pause the video, give yourself maybe 5 to 7 minutes, differentiate in the first example using the chain rule, and use the fundamental theorem of calculus with our new formula in the second. So at this point, hopefully you've given yourself a few minutes to begin working on these problems. If not, this is a perfect opportunity to do so. And in the first one, using the chain rule to differentiate 5 raised to the minus 1 over x, I find that it's challenging to just visualize this at first. So let me go ahead and write some extra details that you most certainly do not have to include, but just to really illustrate how that chain rule is being used. So we can think of this as being a derivative of a composition, f of g of x. And I find in this case that inside function g is maybe something we can pick off fairly quickly. So we have an inside function g of x, which is minus 1 over x. And then we have an outside function. We simply have to think about what is being done to the inside function. So 5 raised to a power. And we can differentiate both of these. The derivative of the outside function would be the natural log of 5 to the x. And using the power rule, the derivative of minus x to the minus 1 would be a positive x to the minus 2, or stated differently, 1 over x squared. So the chain rule tells us we differentiate the outside, evaluate at the inside, multiply by the derivative of the inside. So in our case, this minus 1 over x needs to go inside of f prime. So we have the derivative of the outside, evaluated at the inside, times the derivative of the inside. And just to reiterate, it would have been perfectly fine to jump immediately to this formula. I just wanted to, really be careful to illustrate how we are using the chain rule. For this second example, we can directly apply the fundamental theorem of calculus as long as we know an antiderivative of 10 to the t, which we get using our new formula. An antiderivative of 10 to the t would be 1 over natural log 10, 10 to the t, and by the fundamental theorem of calculus, we evaluate from 1 to 2. So we substitute in that upper limit, t equals 2, minus sign, we substitute in that lower limit, t equals 1. Both terms involve a 1 over natural log of 10. 10 squared is 100, 10 to the first is 10. 100 minus 10 is 90. And this completes our current discussion of investigating these two new formulas associated to differentiating a general exponential or anti-differentiating an exponential. In our next video, we're going to explore a related but new technique of differentiation, something referred to as logarithmic differentiation. So stay tuned and take care.